Hey guys, and welcome back to the lab. Today I'm going to show you how I built an IAM service for LabStore in Go on top of SQLite, covering everything from config handling to proper secret encryption. We'll look into which actions I picked for the MVP, which SQLite PRAGMAs and patterns I used to ensure performance, and we'll even cover a few interesting details on concurrency using buffer channels in Go, a few details on symmetric encryption based on AES-GCM, and even some cool JSON marshaling implementations that arose during development. Let's dive right in. So IAM stands for Identity and Access Management, and it's the place where you go to manage your users, groups, and policies. The policies will determine which resources your users or groups have access to or are denied access to, and these are attached directly to groups or users. In order to define these policies, you have a particular format that AWS uses, which is something similar to this. So this is a policy document, and it begins with a version for the format and then an array of statements. Each statement contains an effect, which can be allow or deny, an action or array of actions. In this case I'm using the action to list all my buckets in S3, and a resource. In this case we are using globbing to match any resources. In this second example, we've got an allow for get and list requests, which means that we'll be able to download and list all files within these resources, so the bucket and all of its files. And we are using the Amazon resource names over here, the ARNs, and we are keeping this compatible with AWS, although we could have used something like the LabStore here, but for compatibility as a drop-in replacement we use AWS still in here. So in order to start our IAM service, we'll need a bunch of configurations that we need to store somewhere, and so let's begin by taking a look at the file format that we designed for this and how we handle it in Go. And so you'll have a .example over here. This one is git ignored, but you just copy it over. These are sensible defaults, so we can use it directly. So we've got for our backend, all of the settings are over here. We now have storage, which defines a data directory, and this will contain both the files, the objects, this is our data directory from before, but it will also contain a metadata directory where we'll drop our IAM database in SQLite. Our files will be dropped under a subdirectory called objects. And then we have a separate keys directory. These two directories are separate because when we deploy this in Docker, we want this to be a separate volume, so it's easier to set it this way. And then we have the configs for our three different services. So we've got a new admin service. It right now only does health checking. But we config those settings over here, but we also config our admin credentials over here. Then we've got our new IAM service, and we'll get to that next, but we've got our older S3 configs over here. As you can see, these follow a pattern for every service. And then we've got a few new settings, and I'll be adding these as I go. For instance, we've got a setting for max keys, and this is a hard limit. So for pagination on S3, at most you can return 1,000 keys. Even if the user asks for more, this is a hard limit. And we've got the buffer size for put objects. It will read this amount of bytes before flushing into disk. And then we've got our main service for today, which is the IAM service. These all run on ports 6789 for S3, 6788 for IAM, and 87 for the admin. In here, as you can see, we've got a bunch of configs for our IAMDB, which is in SQLite, so these are essentially SQLite configs, except for this right shan cap, which I'll get into detail later. We are using cache, we are using timeouts, and we've got a connection pool over here for read connections only. So let's take a look at how we handle this. One detail that is interesting to know is there is a priority system for configs, and this is quite standard, but I'll cover it anyway. So if you go into configs, our lowest priority is our defaults, and they are all defined under config as constants, as you can see here. Then after the defaults, the file will be the config file will be the one that has priority, and over that there is more priority for, or a higher priority for environment variables, and we define those environment variables simply using automatic env. This means that we are in here, we are using Viper. So let me give you a quick run on how Viper works. So as you can see, we've got our types in here. This is the entry point, so our app config. We are only interested in loading the backend configs, so we are loading these ones, and this will have a direct correspondence with the structure that you see here. So for our app config will contain a backend, and then for the backend we have storage, admin, IAM, and S3. As you can see, this uses map structure to load the IAM config. This is a library that SPF13 Viper, which is the library that we use for configuration handling, it already uses map structure because it's by SPF13 as well. And then we have a direct mapping. As you can see, we have a few settings that we don't read directly, we set them internally. For instance, the object's path and metadata path, or the master key path, which are derived as just subdirectories or files within the directory that you set within the config. And then we've got the server config over here, the IAM config over here, our database configs, etc, etc. Then these are just debug messages, but if we go into the load command, we first set the local paths for the files, and we support the local directory, etc, LabStore YAML, and the user config dir, which is usually under your home.config LabStore. Then we set the defaults here, and this is the internal identifier for Viper, so it's the same as the path within the YAML. We set these defaults, and then we set the overrides, so the environment will be the first, the highest priority over the file configs, which already is higher priority than the defaults. And we also use the command line flags as the highest priority one, so if you define anything using CLI args, they will be the ones that set the config. So now let's get into our SQLite database design. As you can see, this is a very simple design. We have a users table, a groups table, and a policies table. That's it. So the policies can be attached to users or groups, and a user is a member of a group, right? Or a group contains several members. And then we've got our policies over here, which contain a policy ID. For the user ID, group ID, and policy ID, we are using the Amazon unique identifiers, so it will be something like this. Essentially, there is a prefix with 4 characters, and then this is we are generating this randomly. It is not known which algorithm they use to generate this, but we are just generating an alphanumeric string after this. So it looks something like this, and if you go into the documentation, you'll see that for users it begins with IDA, for groups AGPA, or for policies I believe there is one as well, which is ANPA. And we are using only managed policies because these are policies that are set on a separate table, like I was showing you. Because you can also have inline or embedded policies, but we do not support that as of now. So let's take a look at our users. Like I said, there is an ID, which is a primary key, a unique name, a unique ARN, and then you've got a textual access key. We are using the username for now, so it's the access key is the same as the name. But this is so that we can later expand this, because we currently only support one access key per user, and this will change in the future. And then we have a blob which contains the encrypted secret key, and I'll give you the details in a moment. Then for groups, we've got only the ID, a unique name, and a unique ARN, and groups are essentially just defined within the junction table for group users that you don't see here, but I'll show you in the schema in a moment. And then we've got our policies, which similarly have the policy ID, the unique name, and the unique ARN. And then they contain a JSON document, which follows the format that I just showed you for the policy document. And then we've got a created at and updated at dates that default to the current date. This is just standard. There is a trigger to update the updated at date. We never touch this directly. So the schema looks something like this. So this is just the tables that I showed you before. Then we have the trigger where we update the timestamp. So anytime there is an update on the policies, we change the updated at date. This is very trivial. And then we've got our junction tables. So we've got our group users. Essentially, we just define the primary key to be this compound primary key based on group ID, user ID. And then we've got foreign keys and this on delete cascade, on update cascade, so that when the user gets deleted, this also gets deleted, and any other dependencies really. And then we've got the user policies, which follows a similar pattern, but it attaches a policy to a user. And then we have the same thing for group policies. And if we go into the code, we can take a look at how this is implemented. So this is implemented under the IAM package, and we've got our IAM store. And as you can see, our schema is defined inline in here. We could have done something like using go embed and then dropping this into a directory over here and setting something like schema string, and then we wouldn't need this. We could just drop this SQL code into a SQL file with syntax highlighting and indentation and all that. But since most of our queries are quite small, they are just basic CRUD queries, this is the only one that is longer. We didn't really do that, but maybe in the future we'll do some refactoring and clean this up. So every time we start our IAM server, we'll ensure the schema exists. This is why we use if not exists, so this can run idempotently. And then let's take a look at how we manage our database connections. So in order for SQLite not to lock when writing or reading, we need to set the journal mode to the write ahead log. So we set it to wall. This is one of our pragmas over here. And then we have a reader connection and a writer connection, because even though we can concurrently read at any time from SQLite when it's in wall mode, we can only use one writer still. right? And the writer, every time someone is writing, it will lock. So we need to handle that somehow. Of course, the IAM service is read heavy, not write heavy. So we can do quite well with SQLite and a single writer at this point. Maybe in the future we'll need to revise this. But anyway, let's get into what all these pragmas mean, and then let's take a look at how we handle writing and how we handle reading through connection pools. So first we set synchronous to normal, and this essentially just controls how often fsync is run. In normal mode, we are ensured high performance and safety if we are running this in wall mode. And since this is not write intensive but read intensive, normal is just perfect. Then we set our temp store to memory, because any temporary tables or temporary indexes will run in memory, although we don't really have any at this point. But in the future we prefer to run this in memory if we use them. We use different cache sizes that we set in our config, like I showed you before, for reader and writer. By default we use 64 megabytes for readers and 16 megabytes for writers. Then we set locking mode to normal. The only other option is exclusive, but we need concurrency here, so it needs to be set to normal. And then we set a busy timeout of 5 seconds, just in case the write connection is not available for 5 seconds, then this will just fail and disconnect, and you'll have to retry. Usually clients retry automatically for you, so this is not a huge concern. So let's take a look at how we handle reads, which is the easy part. So for the read DB, we set the max open connections and the max idle connections to the settings on the config file. So we've got our caches here, like I was saying, and now we have got 3 max open and idle connections for the reader. This should be more than enough. But you can increase this number if you have more RAM available, and keep in mind that the 64 megabytes that we are setting for the cache will exist per connection. This is not shared cache, okay? And then for the writer we only have 1 connection top, because we need to have a single writer. So we have a different way to handle this. So for writers, what we did was implement kind of a queue that we implement using channels. So essentially, let's just take a look at the writer first, which is the main code for this. So we make a channel with type SQL task, and I'll show you what this contains in a minute. And then we set a max chan cap. For our default we use 32 write queries at most. This should be more than enough. And then we just iterate over all our tasks, but within a Go routine. But notice that the Go routine is wrapping the for loop. It's not inside the for loop, so this doesn't run concurrently. It just gets here and gets processed sequentially through the channel. We are iterating over the channel. This will not block and will return the task channel directly, but internally this will block as it waits for new SQL tasks. And we call that task through a function that is defined within the SQL task type, and then we return the response to the result channel that is defined within the task. So let's look at how a SQL task looks like. So it's got a UUID, so we can log this and track this. So we can attach a given SQL task to a particular HTTP request. We also send the context. The context is useful because most libraries in Go user context. And for instance, for SQLite, you can send it the context, the same one that you use on your HTTP request. And if the user cancels the request, then the query will also be cancelled. Okay, unless it already went through, and that's that. But you know, if it's being run, it will get cancelled, and will free up the connection pool. This is very important because of that. And then we define a result channel that is send only of type SQL task result, which only contains, you know, the regular output from SQLX, from running a regular query using SQLX, which is the library that we are using here. And then you define a function, this type SQL function, which gets the context and the database connection, and just returns a SQL task result, the one that you see here. So this will look something like this when we call it. So we already provide wrapper methods, so we don't have to, you know, do this every time. So these are essentially the same arguments that we get in SQLX. So if you look at here at DB, this is a SQLX DB, and you've got exec context, which takes context, a query, and the arguments, which is the same that we send here. So every time we run a writing query, only for writing, we create a new channel with a result channel. It's buffered as a single result because there is only one result here. There will be one channel per task, right? And then we create a new SQL task that we send to the write channel that was created by a new write worker. And then we send it the context, the result channel that we just created, and the SQL function. We send it the database, and we essentially just call exact context or whatever method we need. For instance, in here we use exact context, but in here we've got another one for named exact context. This is just for convenience really, but it's the same thing. And then we return a new SQL task result with the result and the error back to the caller, right? But we should also add a timeout to our buffer channel. This is something we haven't done yet, because if it's full, it will block until there is a slot available to process, right? So like I said, we are using the SQLX library. This is built on top of database SQL, so it's quite standard. And it does nothing much for you except handling the connection pool, and having some utility methods to integrate with types. So they have named exec, named query, where you can just pass it a type, and you can use the fields of the type as your query parameters. So this is just a basic utility. They do nothing much beyond that, and that's how I personally like it. I don't really like ORMs and all that. I prefer to be the one with freedom to handle my queries and write my queries the way I want to write them. Another option would be to use SQL-C, and SQL-C does a lot more of what I just told you I don't like. The SQL-C generates Go code. So you just create your SQL files, you add some comments with the name of the method that you want to create. Usually for CRUD it's okay, but I personally don't like this style of accessing SQL, so I didn't use it. I used SQLX instead. And then this is the library to handle your SQL. Then you need to pick a driver, and particularly for SQLite, and you've got the modern C driver, which is Go native. It doesn't require you to compile anything with GCC or a C compiler in the target platform, so it remains easy to compile. You can compile for Windows, Mac or Linux, all in Linux. The other option would be, and this is faster, would be to use the C driver. But at this point I'm not particularly concerned with speed, but more with development speed and ease of use at this point, because IAM won't have that much read or write load really. We should take a lot of care with our S3 server for performance, but IAM we can be a bit more relaxed with our requirements, so we essentially picked modern C. And as we were doing this, we wanted to make sure that we weren't using the other driver, so Go SQLite 3. And so the way that we tried to make sure was by running rg Go SQLite, and we noticed that in fact the C driver is mentioned on our Go sum. So we wanted to know exactly why this happened. Did we miss it, and as we were testing left it somewhere? So there is the go mod graph command, which let me just show you. Oh yeah, I need to be within our backend. This will show you all the dependency tree for your code. So I tried to search for Go SQLite in here, and in fact it's here, but it still doesn't tell me exactly why it's being used. It says it's a dependency for SQLX, okay, but why am I using it? And so there is a go mod y that you can use, and if you give it the -m and the name of the module that you want to check, it will tell you exactly how it's being imported. So in my IAM package I am importing SQLX, and SQLX has this SQLX test that calls the C driver, and this makes perfect sense, right? Because SQLX integrates with both drivers, it will have tests for the C driver as well. And so this is a tiny tip. If you need to know exactly why something is listed on your Go sum or even Go mod, you can check go mod y and you know, have your answers on this. So now let's talk a bit about security and encryption. For LabStore we use SigV4, and there is a video about this if you want to check it out on this same series, completely dedicated to signature version 4. For computing the signature, we'll need access to the plain text secret key, and so we cannot really hash this beforehand and store it. We need some kind of symmetric encryption to handle it, because we are using as the key for HMAC, and we are giving it the date, and so the date will of course change, and we'll need access to the plain text key so we can run HMAC on top of it every time for each request. So in order to implement symmetric encryption, we use AES with a 256-bit key. This is 32 bytes. And we use a variation called AES-GCM, which uses a nonce. This nonce is kind of like, if you know encryption, it's like a salt. It's something that you add to your plain text to make it random. So for instance, if you were encrypting something without a salt or a nonce, and you know, like 30 users use the same password, it will look exactly the same encrypted, right? And this is a security issue. So in order to avoid that, you add a random string to it, and this is called a salt. And in particular for AES-GCM, you add something that is called a nonce. So it's an added string that is completely unique to that encryption at that time. So it never repeats. And AES-GCM also checks if there is some data that got changed. You can add additional data, not to the encryption, but for the check itself. So we implement this under our security model, under encryption. And this is just using, standard lib stuff from Go, so it's very, very trivial to do. So we first need to create a master key. And let me show you how we do this. So we've got this ensure master key that is run when we start the IAM server. And under security, we've got this generate master key, which just generates a key of 32 bytes, which is the 256 bits. And this is just reading from random, really. And there is no restriction here. We also have a generate password. This has a password char set. This is just plain bytes, right? Once we have this master key, we'll store it under the keys directory that you saw on our config here. So it will be stored under keys/master.key. Then we use this key for encryption in here, right? We just pass the path over here. This comes from config. We see that we call it inside encrypt AS, and we call this, for instance, in here. And as you can see, we are sending config storage master key path, which we set on our config. And so this is essentially just creating the instance for the AES-GCM. We create a new cipher and a new GCM. This one encrypts, this one checks for integrity. And then we take this and we create a nonce. Okay, this is how we do it. It's just reading from random. And then we seal this, which means we encrypt it, but we call it seal because it also computes integrity, right, based on this nonce and other optional. So the last argument is additional data. I don't use any, but you can, and this will be used not to encrypt but to ensure integrity. And then we just encrypt it and we create a blob, a byte array with the nonce and the ciphertext, which we'll then store on SQLite, right? When we decrypt, we do just the reverse process. We get the encrypted blob back, we extract the nonce, we extract the ciphertext, and then we decrypt. Also, just a quick note that for now the IAM server itself is left unprotected. In the future we'll add authentication based on the admin credentials, but for now, if you need to deploy it, and it's really not ready to deploy yet, but if you need to deploy it, you should secure the IAM server behind maybe a reverse proxy. Make sure you have TLS and HTTP auth or something like that, and it should be enough. In the future we'll add authentication with the admin credentials for the IAM server itself. So now let's take a look at how exactly we implement one of the actions for IAM in LabStore. So like I told you before, we've got our store type, which accesses SQLite. It handles all the CRUD operations, and within that store type we've got cached users, groups and policies. We defined time to live, and then we've got, you know, the other stuff that you already know for the reader and writer, and for each action we have a separate file. For instance, for policies we have policies create to create policy, and this will contain our business logic, which is independent from the HTTP request, and the CreatePolicy handler, which implements a call to this CreatePolicy with all the IAM required parameters and response type and errors. Our cached policy, for instance, contains a policy, the time when it was loaded, so we can know when to expire it, and whether it never expires. We needed this in one of our use cases for admin. The admin never expires, so we set it up in memory directly, and I'll show you how in a minute. Then we've got our policy, which maps directly to the database. We've got our policy document, so this is JSON. This will be unmarshaled when read, and it will be loaded into its own type with an array of statements, and these are all separate concerns. Then we've got our HTTP handler, and in particular we have the returned response, which gets encoded to XML, and this just follows the documentation. So the response will contain a CreatePolicy response node, and this will contain two nodes: the response metadata with a request ID, and the CreatePolicy result with the policy that was created. And this is a separate class called policy result just for returning. In the future we might merge the two, but for now we are keeping it separate. And let's take a look at how this looks like in the code. So if we go into store, we won't find it here. This is just the top level for store, but we'll find it under policies create. And as you can see, we've got our response types over here. Our policy type is defined directly in policies because it's shared by all requests. As you can see, this is the mapping for our database, and then we also have a policy result, which is a separate type. These might be merged, like I said, but for now we are using this result method to just convert one into the other. Then for each document we had to define the value and the scan, which are used by SQLite. So when we want to store this to write it to the database, we need to marshal it. This will return the byte string for the JSON, and when you load it, if it's empty, it will return an empty document. If not, it will unmarshal arrays and strings. It will check for the type. This is, by the way, a particular statement that you can run in switch case only. You can do this variable name dot type, and each case statement will match to the type, and the value cast to the correct type will be stored in S. And so this is how we handle serialization into the SQLite database. Then let's take a look at how CreatePolicy works. So let's begin by the HTTP request. So we need a policy name and a policy document. And let's quickly jump into the documentation. You'll find all the actions here, CreatePolicy for instance. And if you go into examples, you'll find an example request. And as you can see, these are all post requests. They also support GET, but most of the times they are done as post requests, and all the clients that I use post requests by default with form parameters. So what you are seeing here are really form parameters, not get parameters, but because it supports both, they just present it this way. And so the way this works is you call the IAM endpoint with an action query or form parameter. In this case it's CreatePolicy, and then you pass all the required parameters for that particular action. For instance, in here it's the policy document, which is the JSON, the policy name as well, which is a name that you just can give it. You can pass the version, but in LabStore we just ignore it because we just support the latest version, not this older one. And the auth params, we don't implement these yet, like I was saying, so this is left unprotected. And then we've got an example response in here, which follows the types that I just showed you. And so once we have those parameters, and unless there is an error, and we are not respecting the IAM format in here, but we should fix this in the future, then we load, we unmarshal the policy document, so we have the correct type, and then we extract the context to send to ultimately to our SQLite, so it can get cancelled like I was telling you. And we call this store CreatePolicy, which is defined in this same file with the context, the policy name that we want, and a reference to the policy document we just unmarshaled, right? And we error handle in here. These are errors that respect the format set by IAM. And if we go into CreatePolicy, we'll see all the details for this. So we generate a unique ID, and this follows the unique IDs by Amazon, the document I showed you before with the prefixes, right? So we just get this unique ID prefix type. It might be, for instance, a user, and if it's a user, we just concatenate this either with a random string over here, right? And so we have a policy ID. We use the name that the user sends, and we also have this toARN method, which generates ARN identifiers, right? And this just takes the ARN type. It might be user, group, policy, or even S3, and the ARN type is this element over here. Okay. We use the default account ID, which is always this one. We only have one. This usually maps to, on AWS, to the user account. So there are many customers to AWS. Each one has their own identifier. That would be it over here. But because this is to be self-hosted, we only have one. In the future, you know, this might be extended as required, but for now, this is how it works. Then we concatenate the ARN type and the path. The path that we use is always the root. We don't really customize paths at this point. We don't pass it as a parameter, although we could extend the API to support this later, of course. And then we just concatenate the username or the policy name or whatever it is. And in this case, we send it the document. Then we've got our query. We just insert into policies the ID, the name, the ARN, and the document. And we run the SQL named exec context. It's named exec because we use the names over here. And then we just use the policy in here. We go into the policy. You'll notice that there are some names defined here, and these are the the names in named exec, not these ones. It's not trying to discover what the names are by these names, but by the DB names that we defined here. These are the mappings to the database. And then this is calling our writer, so it's essentially sending to our write channel internally. But this follows the exact same format as if we were to use our read DB to, which we don't, but to named exact context, this would be compatible, right? And then we just handle errors. We load the policy by ID once we are done. And then we load this we create a cached policy with the current time so that we know when to delete it later. And that's it, a policy was created. Let's just look at how it would get deleted. So I believe when we on policies get, we check whether the policy is cached or not. As you can see in here, we go into cached policies for the policy ID. We check if it's available. If it's never expired or the time is still valid, so it's not over the TTL, we just return it. If it's over the TTL, we just delete this from the cached policies and do regular select and load it into the cache. Now going back into policies create, if you go into the policy document, you'll see that each statement contains an action and resource. These are implemented similarly. That is of type actions. And if you go into actions, we'll find a custom unmarshal JSON, because the action can be either a string or an array of strings, right? So we need to handle that. So first we try to unmarshal a string. If it's a string, we'll add it to an action array and set it. If there is an error unmarshalling this, then we try to unmarshal it as an array, and we just set it directly and return no error. We do the same for resources. It's very similar. We check whether it's a single string or a multi-string, and we serialize it properly. This is how you handle most of these cases in Go. You just define a basic type over, for instance, we've got resources, it's just an array of string, so that you can define a particular method, and this will follow some interface that is defined within encoding JSON. And so we've talked about how to create a policy, one of our SQLite CRUD tasks for the IAM service, but not about how we handle access granting or denial and actual policy checking. So let's take a look into that. So we've got in our middleware, we've got our IAM middleware, which wraps a handler with a particular permission and then just checks for that policy before, letting you through. And if we go, for instance, into our router for S3, we'll find a bunch of routes in here with this, for instance, for get bucket, which lists all the objects within the bucket. We've got our middleware with IAM S3 list bucket. So this is one type of IAM action, that is the permission that we need for this particular request. And then we just call the regular handler, right? In here, we'll run CachedPolicy, and CachedPolicy will just load the current user and iterate over the policies for that user and the groups it belongs to, and it will check whether those policies match the action and the resource. So we'll collect all the actions and all the resources, and then we'll match the action. We use globbing, so we use this glob module by Gobwas, and once we find a matching action, we will return true. We've got our allowed variable, which is false by default. If we find a deny, we return false immediately. If not, we set allowed to true and continue checking, right? Because if there is one deny, that will be highest priority, and this is why we don't return immediately. If we go into the router by IAM, you can also see that it does routing a bit differently. We are handling post requests only in here, and then we are parsing the form so that all the form parameters are available to the handlers. We get the action, and then based on the action, we determine which handler to use, and this is how we go, for instance, into our CreatePolicy handler that you just saw, and then all is connected to this workflow. So first, let's delete our data and keys directory so we can start clean. And now let's just make sure that our backend is properly built and start our backend in debug mode, so we can look at the output in more detail. As you can see, all the configurations that we load are showed in debug mode. So if you need to, try to understand why it's not being properly set or something, you can just run it this way. And now we have 3 servers that run. So we've got our admin console in here just for health checks. We've got our S3 compatible API on port 6789. This is your main service for LabStore. And you've got your IAM server listening on port 6788. So now let's go and try to run our backend test IAM. I've got, let's run the group policy, which runs multiple IAM actions in one go. Okay, and everything seems to have run properly. And let's just go through what happened here. So first we are creating the user, and this does not give you credentials at this stage, just creates a user ID. And I just noticed that this should be capitalized, it should be all uppercase, but we'll take care of that later. Then we create an access key for this user, and we'll need to copy this to use below, because we are going to try and connect this using these credentials. Then we create a test group over here, and then we add the user to the group with add user to group request, I believe. And finally we just create the policy to be able to read and download from this test bucket and attach that policy, you know, create a policy and then attach that policy to the user. So we've got our alias for LabStore. So we've got our, let me just check alias. We got our alias for LabStore set in here. It's still for a previous test user. So let's just alias set to admin for now. Okay. So if we run this LabStore, let's just check what we have here. We've got the test bucket. Let's also create a sandbox bucket, and maybe let's create a random file called sandbox data that we are going to copy into that bucket, which the user won't have access to, so we can properly test permissions. So we just copy this, and if we ls sandbox, we'll find this sandbox data in there. If we ls test bucket, it's empty for now. So let's also create a random data file that we are going to copy to our test bucket. Okay, and now if we ls test bucket, we'll find random data. Okay, so let's switch into our test user. Now I've copied the key previously and it switched perfectly. So now let's try to ls into sandbox, which we don't have permissions to, and as expected we get access denied. Let's try to ls into our test bucket, and this is working as expected. We can also, you know, copy the file random.data to download.data, let's say, and you can copy it. But if we want to do the opposite, so if we want to copy download.data into LabStore test bucket, we won't be able to, because we don't have put object permissions. As you can see, permission denied, and our IAM service is working as expected. Of course, we still need to properly test security and try to run a pen test on this and see if everything is working, although it's a bit soon, but maybe I will try to find some security YouTuber that wants to do some collab and do a proper testing on top of LabStore. And just a quick one before I go, let's just go into our IAM database and take a look. Okay, so I don't need this running anymore. So we've got our schema over here. So we created a user, so let's select from users. As you can see, there is the test user over here with all the data. There is an encrypted password. If we go into groups, we'll see there is a test group. If we go into group users, we'll see there is a relationship between these two. If we go into policies, we'll find the policy that we uploaded. And if we go into user policies, or maybe group policies, because that's what I was using, you'll find this policy attached to that group. And there you have it. Hopefully you found this video useful. The next one will be all about designing command line tooling in Go using SPF 13 Cobra. Until then, I'm off for a break during the holidays, so I'll see you in 2026. Hopefully it's a very year for all of us, filled with knowledge, system building and overall constructive events. As usual, this week's blog post is available at datalabtechtv.com with a lot of extra details on how to implement IAM, so be sure to give it a skim. I'll be around on Blue Sky for updates, and you can join our community in Discord as well. Don't forget to drop a like and subscribe for all things data. See you in 2026.